Good morning children, welcome back once again to my maths class. In today's video lesson, we will be talking about the fundamental theorem of arithmetic. Okay? Before going to that, we will have a quick recap of the previous knowledge. What are the prime numbers? For example, prime numbers are the numbers which are having factors 1 and itself. Yeah? So let me take some numbers 2, 3, 4, 5, 6, 7, 8, so on. Prime numbers are 2, 3, 5, 7, so on. They are having factors 1 and itself. Then what are composite numbers? The numbers greater than 1 and which are not prime numbers are called as composite numbers. That means here they are greater than 1, 4, 6, 8, so on. For composite numbers, they are having many factors. For prime numbers, the factors are 1 and itself. So, with this concept, let's go quickly see this theorem, fundamental theorem of arithmetic. What does it state? Every composite number can be expressed or you can say factorized. Every composite number can be expressed as a product of primes and this factorization is unique. Okay, this factorization is unique apart from the order in which primes occur or primes are placed. Primes means prime numbers, right? See, every component. For you to make you understand this theorem, I'll take one example. Let me take one number 2310. I'll find out the factors. So let's start with 2 ones, 2 ones, 2 5s, and again 2 5s. Okay. Will this number go with 2 again? No, because the last digit is not 0, 2, 4, 6, 8. This is a divisibility rule for 2, isn't it? So the last number is 5. It doesn't go with 2. So let me take the next prime, that is 3. But I'll check whether this number will go with 3 or not. See, sum the digits. 5 plus 5, 10, 11, 12. If you sum the digits, the number is 12. 12 is divisible by 3. So this number goes with 3. So 3 3s are 9, 2, 25. So 3 8s are 24, 1 15. So 3 5s are 15. Again, let me check will this number go with, it doesn't go with 2, isn't it? So it will go with 3 or not? We'll see. 8, 5, 13, 13 plus 3, 16. 16 is not divisible by 3. So this is not divisible. So let me take the next prime, that is 5. 5 7s are 35. 3 5 7s are 35. Now the next prime after 5. 7. So 7 11s. Again 11 ones. These are the primes which I've got for this. So we have got this primes. So we note it down. 2, 3, 5, 7 and 11. Okay. One of your friend might have got some other primes. He may tell you that he got 5, 7, 3. Okay. Likewise. Another one may have got like in this pattern. Okay. Likewise. See, in all these 3 patterns, you can clearly see that the factors are same. 1 and only 1. The The factors are 2, 3, 5, 7, 11, 2, 5, 3, 7, 11. So the factors are same, but the order placed are different. Here the placing of order is somewhat different. You can take many permutations, but your friend has not got another factor like 13 or 17 or something like that. They have got the same prime factors, but the order is being changed. So what does the theorem tell us? That it is a product of primes and this factorization is unique. That means unique. It is having only 2, 3, 5, 7 and 11. That's it. In this, the products are unique, and from the order in which the primes are occurred, apart from the order may be something here and there, but they are the unique factors of this. And if you see this is a composite number. Yes, because if you see 0 means it is divisible by 10. 10 means 2 and 5. So the factors other than 1 and itself, it is having 2, 5 and all that, isn't it? So it is a composite number. And what we got? Product of the primes. So every composite number can be expressed as a product of primes, and the factorization is unique apart from the order in which the primes are occurring or placing. So for this they have set, for our convenience sake, a standard is set. What is the standard? Standard is that, this is only for our convenience sake. Standard is that they are placed in the ascending order. In the ascending order. That means, see here, 2, 3, 5, 7, 11. In the order from small to the big, from least to the highest. That is, the primes are placed in the ascending order. I could have taken here, this is divisible by 5. Here I could have used 5 to resolve it. Again, here also I could have taken 11. Instead of 7, I could have taken 11. But I haven't done that because I have followed a pattern, that is from the smaller prime to the bigger prime. For our convenience, we have to use this. This is a standard set. That is, every composite number expressed as a product of primes. This prime factorization is unique and apart from the order in which it is placed. And also we have to see that these primes are in the ascending order. So this one problem I have taken down from the do this of your textbook. So please pause the video, note this down, and if you want, you take this screenshot. Okay. And one more thing, we will be finding the LCM and HCF using this factorization. Okay. Let's see. Find HCF and LCM of the numbers 12 and 18 by prime factorization method. Okay. We will be making use of the theorem. This is one example problem from your textbook. Okay. First, let us write down the factors of 12 and 18. Okay. 12, 2 2s are 4, into 3, 12. Factors of 18, 2 9s are 18, so 3, so 3. These are the factors of 12 and 18. By prime factorization method, we have to find out the HCF and LCM. So you have learned HCF, LCM in your 6th class, isn't it? Now here, HCF, how to find this HCF? This is the product of least exponents to the common prime factors. Okay. Whereas the LCM is the product of here least, here greatest. Let's take greatest exponent or the biggest exponent to each prime factor involved. So let me explain you. HCF is the product of the least exponent of a common prime factors. So for this, when you are taking these to 12 and 18, so here 2 are, the power is 2, 3, 1. Here 2 into 3 square. I have written it in the exponential form. Right. What is HCF? I need to find the HCF of 12 and 18. What we have written? The least exponent of the common prime factors. First let me write the common factors. Common are here. This is common 1 and 2 is not here. 3 is common. These two are only common factors. For that what I have to write? The least exponent. The least exponent here is, here 2 is there, 2, 1 is there. So 1 is the least one. Here 3, 1 and 3 to raised to the power 2. So I have to take the least exponent. I shouldn't take the greatest exponent. So the least exponent I have taken. So 2 into 3, 6. So 6 is the HCF of 12 and 18. Likewise, LCM of 12 and 18. What we told, the LCM is the product of the greatest exponent of the each prime factor. Here you remember, here we have noted common, here each and every, that means, and here least, here the greatest. So for each prime, I'll write all the primes involved here. 2, what are all the primes here? 2 and 3. That's it. We don't have 5 or 7, isn't it? And the greatest exponent we have to write. The greatest exponent of 2 here is 2. And the greatest exponent of 3 here is square, 3 square. That comes up to 4 into 9, that is 36. Okay. So we are writing all the prime factors. For that we are writing the greatest exponent. Here we are writing the common factors. For that we are writing the least exponents. That is the difference between HCF and LCM. So for you to understand, let me tell you one simple thing. Explanation. Let us find out the HCF. Okay. For the same thing, 12 and 18. First, I'll write the factors of 12. What are the factors of 12? It goes with 2. It goes with 1. It goes with 2. Because 1 is a factor of all numbers. 2 6s are 12. 3 4s are 12. 5, it doesn't go. Okay. 4, yes. 4 3s are 12. 5, it doesn't go. 6. Okay. Then 12. These are the common factors of 12. Let me write down the factors of 18. Okay. First 1, it goes with 2. 3 6 are 18. 4, it won't go. 5, it won't go. Again 6, will it go with 4? No. 5, 6. 6 it will go. 7, 8, 9, 10, 12 it goes. No. 18 last. So the factors of 18 are 1, 2, 3, 6 and 18. Where are the factors of 12 are? And okay. 9 also it goes, isn't it? 9 2s are 18. And then 12. So these are the factors, just common factors. Now these are the just factors of 12 and 18. I want the common factors. Common factors in these two are 1, 2, 3 is common, 6 is common. Okay. So these are the common factors. But I want the highest common factor of 12 and 18. What is the highest one here? 6. So the highest common factor is 6. So that we got here, isn't it? This is a simple way to understand. Okay, let me take one more simple example for LCM. Let me take 2 and 3. I'll find the LCM of 2 and 3. LCM means least common multiple. Okay, multiples. I'll write multiples with which the number is being multiplied. That means multiplication table itself. For 2, multiplication table, 2 1s, 2 2s are 4, 2 3s are 6, 2 4s are 8, 2 5s are 10, 2 6s are 12, so on. Multiples goes on. Okay. 3. For 3, 3 ones are 3, 3 2 6, 3 3 9, 3 4 12, 3 5 15, 3 6 18, so on. Many we can write multiples. But what we want? Common multiple. First let me see the common one. 2 is there? No. 6 is common, right? And also here 12 is common. If you write more multiples, some more common multiples you will be getting. Okay. But I need here the least common multiple. So many multiples are there which are common also, but the least common multiple is 6. So the LCM of 2 and 3 is 6. Okay. Check it out. For LCM of 2 and 3 is 6. I am taking only the least one. Here I am taking the highest one. So like this, we can find the LCM and HCF of any two numbers or more than two numbers by prime factorization method using the theorem. Okay, this problem is there in your textbook for example problem. So please note down, pause the video and note down. Then we'll see another problem. See one exercise problem. Find the product of its prime factors, express them into the prime factors. So 150, 140. Just expressing them into prime factors. So let's start with the smallest prime, 2. 2 sevens, 2 zeros. Again it will go with 2. So 2 threes are, 2 fives are. So will this go with 2? No. So go for 3. 3, 8. Add these two, 8. So 8 doesn't go with 3. So let's go with another next one, 5. 5 sevens are and 7 ones. So just expressing it in the form of primes, that is 2 square into 5 into 7. So let's see one more problem in the textbook. Find the LCM and HCF of the following integers by the prime factorization method. Let me take one problem. 12, 15 and 21. Is it 12, 15 and 21? Find out the HCF and LCM through prime factorization method. So first we'll find out the factors. First we'll note down the factors. Okay. For 12, 2, 2, 3. 12. Okay. Now 15 is 3 into 5. 21, 3 into 7. These are the common factors of the primes. Now, I want the HCF. HCF of 3 numbers here. 3 numbers. Okay. What I told the HCF is that it is the least exponent of the common primes. So, the common primes. What are common in both, all the 3. Not only 2 or only 1. See, 2 value is not here and 3 is here and here. 5 is not here and 7 is not here. So, you have to take common. That means only 3 is there common in all. So, this is the common factor. And we have to write the least exponent. So, maybe in something you will be getting 2 3's. So, here only 1. So, least exponent is 3 2. So, 3 is the HCF of 12, 15 and 21. And let's see the LCM. What I've told the LCM. LCM is you have to note down all the factors. 2, 3, 5 and 7. See, I did not take the common ones. I have taken each and everything. All factors which are involved. 2, 3, 5, 7. Okay. And what we have to write? The greatest exponent for them. Here, I'll write it in the exponential form. 2 square, 3. 3 into 5, 3 ones, 5 ones, 3 ones, 7 ones. Okay. So, we have to take first all the factors, then we have to take the greatest exponent. The greatest exponent of 2 is 2 square. The greatest is only 3 to the power 1, 5 to the power 1, 7 to the power 1. Okay. See this and write the exponents. Now here 4, 3, 5, 7. It comes 4 3s are 12, 12 5s are 60, 60 into 7, 420. Okay. So, the LCM of 12, 15 and 21 is 420, whereas the HCF is just 3. So like this you can solve. There are 5 problems in your exercise, same based on the prime factorization, and here also there are 4. So take them as your assignment or like your homework and practice them. Okay, let's see another problem. So there's a problem in the exercise. Check whether 6 to the power of n can end with 0 for any natural number n. So the natural number n that is having, it will start with, so any natural number you can take for the number 6 to the power of n, so that this number is having 0 in the units place. Okay. Can end with 0 means in the last digit, that means the units place is 0. You have to check it for the natural numbers. Let us take this. These are natural numbers, but here given for n natural numbers, small n given. Okay. Let me take n value 1, 2, 3, so on. Let me check. I'll substitute n value. N is equal to 1. 6 to the power of 1 is 6. N value 2. 6 into 6 is 36. Now n value 3. 6 raised to the power 3. 6. 6. 6. So it comes up to 216. And n value is 4. 6 to the power of 4 comes to 1296. See, likewise you can take. So observe here, the last digit is 6 in all the cases of 6 to the power of n. But here given that, will it end with 0 for all the natural numbers, for any natural number? Here it is not ending with 0, it is ending with only 6. So this statement is wrong. Also we can say that any number, if you take any number 350, if it is ending with 0 means it should be multiplied. So it is divisible by 10, isn't it? 10 means 2 into 5, the factors. Okay, if it is ending with 0, it should be divisible by 10. That means the factors are 2 and 5. But here if you take 6 to the power of n, here the factors of 6 are 2 and 3, isn't it? It's not possible. Here the numbers ending with 0 should have factors 2 and 5. But here we are having, here we got for 6, 2 and 3 are the factors. For 10, 2 and 5. So this is not possible. That means the number 6 to the power of n can not end with 0 for all or any natural numbers. Okay, understood? So note down this problem. Pause the video and note down this problem, and like this you do the problems in the exercise. If you have any doubts, please write it in the comment box down the video. Okay, tomorrow we'll be learning about the different theorems of decimal expansion. Okay, thank you all.